Good morning to everyone. Today we are going to learn about isothermal irreversible expansion work of an ideal gas. In last class we have learned about the isothermal reversible expansion, and today we will be learning about the isothermal irreversible expansion work for the ideal gas. Previously we learned reversible, that means the change was in very small steps and with very long time. But irreversible steps or irreversible process, as we have discussed about the irreversible process, that is with very rapid or very long or large steps. So that cannot be go back easily in the initial stage. So today we will learn about the irreversible expansion work of an ideal gas. Then we will learn about the maximum work done in a reversible expansion. So how much work can be performed when the process is in reversible? So maximum work, how we can define or how we can estimate the maximum work done in a reversible expansion. Then the main topic of this chapter, the first law of thermodynamics. So we will be focused mainly the first law of thermodynamics in this chapter, and the chapter name is thermodynamics. However, we are going to learn about mainly the first law of thermodynamics, and then we have several definition of the first law. We can define in different aspects or considering different idea. So we will define several definitions, and then we will mention some different forms or special forms of first law of thermodynamics, and then if we have some time, then we will try to understand some mathematical problems. If we cannot cover it all of them today, then mathematical problems or whatever maybe we will cover in the next class. However, let's start with the isothermal irreversible expansion work of an ideal gas first. So in last class we have, at the end of the last class, we have learnt about the isothermal reversible expansion. So in that case we had a system, maybe I can show you again, that this is our last class what we have learnt about the isothermal reversible expansion of our ideal gas. So here we have considered this expansion. Just need to understand all the terms. Isothermal, that means no change in temperature. Isothermal. So when we are doing the process, that means reversible, so that is you are familiar, when a process changes with very long time or very slowly in very small steps, in that case we can reverse the situation and we can come back to the initial position. That is considered as reversible. So two word has two different meaning. Isothermal, reversible. Isothermal means there will be no change in temperature, and then reversible, which can be reversed. And then expansion, that means we have a certain amount of gas and then we want to expand it. So this is our initial position and then this is our final volume, so we are expanding. So isothermal reversible expansion. So reversible expansion work. So how much work it is done when we expand a certain amount of gas in the isothermal and reversible conditions, and for what gas? For an ideal gas. So this is one sentence, but there are a lot of idea in between inside the sentence. So if you can understand that sentence perfectly, that means if you know the terms individually, in that case you can easily understand what we are going to define or what we are going to estimate. So here we have the initial position, initial gas, the volume of the gas, and then if we change the volume isothermally, that means no change in temperature, that means we need to reduce the pressure so that we can increase the volume. So we can, on the other way, if we increase the volume, the pressure will be decreased. So that we are doing here very small steps. What is the steps? DL, the very small steps DL, and then we are doing the integration to get the total area, and then the work done in the total system from initial to final, that means volume V1 to V2. Now if we consider some irreversible process, that means rapidly. Here we have changed the volume just little bit, many fractions, and then we are coming to the at the end. But in case of irreversible process, rapidly or drastically we will move the volume, or we will increase the volume from V1 to V2, and suddenly the pressure was initial pressure was P1, and then the final pressure will be P2. So that is the difference between. Then now we need to calculate how much work we have done during the reversible process and irreversible process. So yesterday we have learned about the calculation how much the work is done during the reversible process or this process, and that we have found the total work done equal W equal minus 2.303 nRT log P1 by P2, or in other aspects we can represent W equal minus nRT ln V2 by V1. So in terms of volume or in terms of pressure, we can estimate the total work done for the reversible isothermal expansion work for an ideal gas. Now we will calculate how much work is done when the process is in irreversible. If the process is in irreversible state, that means the volume will be changed drastically and that cannot be come back easily. So let's see, suppose we have an ideal gas contained in a cylinder with a piston. Last class we have mentioned frictionless piston. So actually we do not have any frictionless piston. So today we are not going to mention the frictionless, just we will mention a piston. This time the process of expansion of the gas is performed irreversibly, just rapidly or instantaneously, by instantaneously dropping the external pressure Pext to a final pressure P2. So initially the pressure was P gas. So if you want to put, or if you want to keep the piston at this position, you need to apply certain pressure exactly to P gas, or inside how much pressure inside you need to apply exactly that amount of pressure. That can be P1 or Pext external. So we can consider. Now if you immediately or if you drastically increase the volume, so from here to here, now this is our total volume of the system, and previously it was only this part. So now you have increased the volume from here to here, so the pressure will reduce quite a lot, and that pressure becomes P2. The work done by the system is now against the pressure P2. Now how much work you have done? So now this is the pressure or total pressure P2. So the work done against the pressure P2. So there is no intermediate terms. Now this is the only pressure, final pressure. So the work done by the system is now against the pressure P2 throughout the whole expansion and is given by the following expression. So just the V1 to V2, initial volume V1 and final volume V2, and the step, this is the dV. So P external W equal minus P external integration limit V1 to V2 dV. So the P external what? P external just P2. So we are keeping the value P external like as P2, and here V2 minus V1. So volume V2, here P external minus P external V2, sorry, V1 to V2. Now we are writing just V2 minus V1. So how we are writing V2 minus V1? So P external, now V1 to V2. Previously volume V1 was, V1 is small and V2 is bigger. So V2 minus V1. So limit like this way, and the external pressure. So P2 dV. Now this sign, how the sign is inversed? Minus P external. The P external, this is our, when we are considering the system is expansion. That means the work done by the system, that sign is considered as negative, and if we consider the work is done by on the system, then it is positive. So now the pressure, this is on the by the system. So now we are calculating this pressure, this is inside pressure. So to keep the cylinder in this position, how much pressure you need to put? If you do not put some pressure from the above, in that case you are applying certain pressure to the piston, so that the piston remains here. So you need to work. Okay, you cannot understand. So previously we have mentioned that the sign, what is the sign for the pressure? The sign for the work done. If the work done by the system, in that case the sign of the work is negative. If the sign work is done by the system, then the sign is negative. So how much pressure it exerts, our external pressure, how much? That is, this is our, so we are using negative sign for the external pressure, the work done. Now we are in the situation where we need to think about that the piston, if you reduce the pressure, as you have increased the volume, so the pressure has been decreased. Now we do not have individual steps for like as reversible process, so that we cannot go back. Now the pressure has been decreased quite a lot, and we are applying certain pressure exactly to the pressure what we have this direction. That means here we have the pressure P2. However, if you need to fix the piston in this position, you need to apply certain pressure to the on the system. You need to apply the pressure on the system, so that the piston remains here. Now you are working. Now we can consider by this way, that is also okay. But if you consider the work is done by this pressure, that means this is the pressure. How much pressure we need to apply? This is the P2 pressure. So you need to apply the P2 pressure on the system. So the work is done on the system. So we are applying the sign positive. So therefore the delta V, what? The delta V is the V1 to V2. That means the difference between V2 minus V1. That is considered as delta V. So the sign is positive, and then we are writing the V2 minus V1. There is no individual steps, so we cannot consider very small steps. We don't need to find out the integration, just the difference between the final volume to initial volume. So this is our work done for isothermal irreversible process. Now if we consider what is the maximum work done in the reversible system and irreversible system. In the reversible system, we have considered that we are changing the pressure or volume in very small steps. So let us consider this is our initial volume and this is our final volume. So from initial to final volume, to go from the initial to final volume, the pressure, the pressure of the system, initial pressure was this, and finally the pressure decreases up to this. So we are integrating and getting the total work done, which is defined by this way. So this shaded area, when we integrate the total, that means the V1 to V2 PdV, in that case the PdV, how we can get, just getting the total area of this region, that is the maximum work done in the reversible system. But in case of irreversible, process, we are doing just the work rapid process. When the volume is V1, volume increases from V1 to V2, and the rapidly pressure falls from P1 to P2, that means this volume, this pressure. So we are not considering the work done in this region. So irreversible, in case of irreversible process, the work is only this region. That means the change in the pressure and volume, or the work change in the pressure volume, in terms of pressure volume work, while the final volume and final pressure. So in between this shaded area is the maximum work done in the irreversible process, and this is the maximum work done in the reversible process. Now we will see very little mathematical problem. 1 mole of an ideal gas at 25 degrees Celsius is allowed to expand reversibly at constant temperature. That means constant temperature, that means isothermal process. So 1 mole of an ideal gas at 25 degrees Celsius, and already mentioned at constant temperature, the temperature will not change at all. So at 25 degrees Celsius it is allowed to expand reversibly. That means reversible isothermal process. That means in previous class or yesterday we have learned about the reversible isothermal process. So the gas is expanding. 1 mole of gas, that means value of N would be 1. 1 mole of gas, ideal gas, at 25 degrees Celsius is allowed to expand reversibly at constant temperature from a volume of 10 liter to 20 liters. Now you know the initial volume and final volume. Now you have to calculate the work done by the gas in joules and calories. You know the formula. Work done in the isothermal reversible process, reversible process for ideal gas, W equal minus 2.303 nRT log V2 by V1, or we can write down minus nRT ln V2 by V1, like this way. This is the formula. Just we need to use, if you can calculate by using any formula, using ln or log, doesn't matter, because nowadays you have calculator, so you can use ln or log, anything. But previously people could not use the ln, so they have converted into log, and then they have a very big log scale. This is a very big chart, so you need to find the value of log and then you need to write down the number. But nowadays you have calculator, so just you can use your ln or log, whatever you can. So you can use any formula, just anything is fine. So just use the formula correctly and sign you need to. This is the isothermal reversible expansion. So in last class we have shown that in case of isothermal reversible expansion we get the sign negative because the work is done by the system, therefore the sign would be negative. So the formula is this, and now just put all the values. What are the values? N, value of N is 1. This is the 2.303, and value of N is 1, and this is the value of R. R. This is in SI unit, and this is the temperature 298 Kelvin. This is 25 degrees Celsius. If you convert into Kelvin, so you can convert into 298 Kelvin, and the log volume V1 is 10 and V2 is 20. Just we know all the values, just calculate into, then you will get the value in joule, 1717.46 joule. Now divided by 4.184, because we know 1 calorie equal 4.184 calorie. So for 1 calorie equal 4.184 joule, therefore divide by that number, you will get the work done. So I have done mistake here, so that should be here. Okay. So this is the work done, so that is the value. So this is very simple mathematical problem. Now another problem, very similar. Find the work done when 1 mole of gas is expanded reversibly and isothermally from 5 atmosphere to 1 atmosphere. So that means you have given the pressure. Now the volume is not given. So we know the formula for isothermal reversible expansion of an ideal gas in both the forms, like as pressure or volume. So now find the work done when 1 mole of the gas is expanded reversibly and isothermally from 5 atmosphere. That means previously the pressure was very high and now the pressure has been decreased to 1 atmosphere, therefore the volume has been expanded. So this process also a isothermal reversible expansion of an ideal gas. So we should use the form in terms of pressure. So write down the formula, W equal minus nRT into ln P1 by P2, or even you can write down minus ln nRT. So anyone can have the formula like this way, just minus nRT ln minus nRT. If you write down, check, you can someone check what we are going to have here. If you write down minus W equal minus nRT 2.303 nRT, then log, use log. I have calculated using this formula. Now you calculate using this formula and give me the number. If this number or this number is exactly same what I have used here. Anyone? I think you have calculator in your hand. So just calculate 2.303 nRT log P1 by P2. So I have calculated using this formula, minus nRT ln P1 by P2. Now you will use this formula, minus 2.303 nRT log P1 by P2. Here n value of n is 1 and R value of R is 8.314, temperature 298, and then ln 1 by 5, because initially the pressure was P1 was okay, P1 what was isothermally, P1 by P2, okay, from, if I did mistake, formula P1 by P2. Let's see what is our formula.
So P2 by P1 হবে মনে হচ্ছে।
One second. No, P1 by P2, or let me check, I have the book. Maybe during
Sir, book P1 by P2 লেখা।
Okay, then
page 270.
Page 272, that cannot be matched with my
270.
That will not, that will not match with me because I have maybe different version. So if you say, yeah, this is P1 by P2. So initial pressure how much? 5 atmosphere. In that case, isothermally, the expanded reversibly and isothermally from 5 atmosphere to 1 atmosphere. In that case, we should have the P1. P1 is 5. Is it? Yes, P1 is 5. So that is okay. So what I have given here, that is also same. Okay, P1, that should be not in terms of ln. In this book they have used log. Okay, yes. One thing, in terms of ln P1 P2, that is also okay.
Sorry.
I think I have did this mistake. 5, it should be just 1. Okay, that is perfect, because I have considered the value other way, or during typing mistake I did mistake. So that is the ln P1 by P2. So initial pressure is 5 and final pressure is. So now calculate. You calculate the value what I have found by this way, and now I need to check if I did the total result.
Sir, ठीक है sir.
What is the book named? This is just from the physical chemistry, essentials of physical chemistry, ball and ball, or ball and tuli. So you have checked from this formula also. Anyone? If you put 2.303 nRT log P1 by P2 or minus nRT ln P1 by P2, you will get the same result, because both are in same form, just we are converting ln to log. So that will be perfect. So this is the mathematical problem, that will be very simple. Now we will go to the most important, another thing, something remaining, internal energy. So we have one another term, internal energy, that is very simple. But sometime we may define internal energy, but we will mean many things. That means for a molecule, if you consider a molecule, it has different types of energy. What types of energy? It can have kinetic energy, potential energy, and vibrational energy, and different types of energy. But if we want to mention some internal energy, if we do not define specifically the kinetic energy, vibrational energy, potential energy, anything, if we do not define that types of energy, then if we define the energy or internal energy, you will understand the summation of all kinds of energy. So the total of all possible kinds of energy of a system is called its internal energy. Any types of energy inside a molecule or inside a system. So if a system has millions of molecules, in that case all the molecules are vibrating continuously and they are moving for forward, backward, or reverse way, or any other way. So they have these types of energy. Even some of them can be rest for a very short period of time. In that case they will have some static energy or some potential energy. In that case, if we want to define the internal energy of a system, in that case you need to think about the sum of all possible types of energy. Until and unless we define the energy, in other word, if we define the kinetic energy of a molecule, in that case you will understand the kinetic energy. But if we consider the internal energy, or if we define internal energy, then you will understand the internal energy, or that means the sum of all forms of energy in the system, or all the molecules. So the word internal is often omitted, and energy of the system always implies internal energy. So most of the time we do not use the internal word, just we use the internal energy or just internal. So just energy, if you consider energy, you will understand the internal energy, and internal energy means the sum of all forms of energy in the system. So the internal energy of a system like temperature, pressure, volume, etc. is determined by the state of a system and is independent of the path by which it is obtained. Hence, internal energy of a system is a state function. So a state function, in one of the last classes, in the maybe first or second lecture, I have mentioned about the state function. If any parameter or a component or property do not depend on the amount of the substance, if the property do not depend on the amount of the substance, then it is considered as a state function, and if it is changed with the amount, then it is not a state function. Okay, first law of thermodynamics. So that is the main topic of this chapter, and we will learn many things regarding this. So, and also we will learn different definition or different form of first law of thermodynamics. So, and also we will calculate or we will learn different mathematical problems, how we can calculate the work done in different systems. So let's start the first law of thermodynamics. What is the first law of thermodynamics? So the total energy of an isolated system. This is a system. So this is our original position, and this is the final system. So if you increase or if you heat the system by somehow, you can use some heater, you can use some lighter, or you can do some chemical reaction inside, so that the volume of the system can be expanded, but the system remains same. So that means this is an isolated system. Isolated system, that means I have defined three different types of systems: isolated system, open system, and closed system. In the first class I have defined, if many of you was not present in the first lecture, so I would recommend you to see or to watch the video, YouTube video. In the first and second lectures already I have given you the videos. So if you are not familiar what are the isolated system and closed system, just I am going to give you the just a simple definition. So if this is a system, this is our boundary, and this is our system. If some energy or matter, both of them can be transferred from the system to the surroundings, this is our system, and outside is our surroundings. So if we can have a system, like this, the matter, that means inside substance, and the energy both can transfer from system to the surroundings, is known as open system. And if the substance cannot transfer, only the energy can transfer, in that case that is considered as closed system. And if neither heat nor energy or nor matter, that means heat or energy, anything, both are same. So if the energy and the matter, none of them can transfer from the system to the surroundings or other way, that is considered as isolated system. So here we are going to mention about the isolated system. So when you heat or when you apply some energy to the system, so it will perform some work. How much work is done by the system is exactly equal to the increase in the internal energy and the work done by the system due to the change in volume. So how much? So the total energy of an isolated system remains constant, though it may change from one form to another. Actually, this is not the definition what I have mentioned. When a system is changed from a state to a state A to a state B, this is our state A and this is our state B. So when a system is changed from a state A to a state B, it undergoes a change in the internal energy from EA to EB. That should be in a smaller as like this way. When a system goes from a state A to a state B, then their energy changes from EA to EB. Thus, what is the change in the internal energy? The change in the internal energy would be just delta B minus delta A. Delta B is the final or the energy of the final state or final position, and this is the EA is the energy of the initial state. Now, how we can define the how much energy is there? So if you put some energy or if you put some heat to the system, then it will perform some work. It will perform some work that can be, this is the isolated system, so no heat or energy can escape from the system. So it will perform some work. How much work it has been performed due to the change in volume delta V? That will be W. So the work done, so the delta E, the change in energy, how much energy is changed, that will be how much energy you have supplied minus the work done by the system. The amount of work what it has been done, it did, so the amount of work is exactly, so the change in energy will be the amount of energy you have supplied, the supplied energy minus the work done by the system. This is the W. So the change in energy will be the exactly the subtraction between the supplied energy and the energy performed, energy loss due to the work done by the system. So this energy change is brought about by the evolution or absorption of heat or by work being done by the system. Because the total energy of the system must remain constant, because this is the isolated system, there is no way that the energy can go out of the system. So the energy, the total energy of the system will remain same, but it is converting from one form to another, because one form is the total energy what we have given, this is the Q, this is the total energy we have given Q, and the other work we are getting the energy as the work done energy. So the total energy of the system will be exactly what we have given, or the total energy of the system will remain constant. We can write the mathematical statement of the first law as delta E equal Q minus W, where Q is the amount of heat supplied to the system and work equal W equal work done by the system. So easily we can define the first law in another way. The net energy change of a closed system, not a closed system, it should be isolated system, should be isolated. In an isolated the net energy change in an isolated system is equal to the heat transfer to the system minus the work done by the system. So as much as you supply, this is the total energy you have supplied, and the work done by the system, that is W. So the net change in energy, how much energy is changed, that is delta E equal the amount of energy supplied minus the amount of work done by the system. This is the definition of first law of thermodynamics. The net energy change of an isolated system is equal to the heat transferred to the system minus the work done by the system. Let us consider the system expanding hot gas. Hot gas, that means what we have given. This is the, if we consider that figure, this is a gas and we are if it is a hot gas, so what will happen? The hot gas will try to expand automatically, so it will expand and it will increase the volume, so it will perform some work while the volume is changing. Therefore, what will happen? Some of the energy will convert into the work while it is increasing the volume. So some of the energy will be converted to change in the to work to increase the volume. Therefore, the internal energy or the heat of the hot gas will be changed or decreased. The gas expands against an applied constant pressure by the volume delta V. The total mechanical work done is given by the relation W equal P into delta V. So work done due to expansion, yesterday we have learned the PV work energy or pressure volume work. Pressure volume work is just pressure multiplied by the change in volume. So W equal P into delta V, pressure multiplied by the change in volume. So previously this is our equation, delta E equal Q minus W. Now if we put the value of W like as P into delta V, so we can write down delta E equal Q minus P into delta V. So here you can see delta E equal Q minus P into delta V. So this is another form of our first law of thermodynamics. Some other definition we can have several definitions of first law of thermodynamics. Whenever energy of a particular type disappears, equivalent amount of another type must be produced. So in any isolated system, like as we have mentioned, if we have a hot gas, so what will happen? If you keep a hot gas inside a cylinder or a certain volume, in that case it will try to expand the volume. But while it is expanding the volume, so to change the volume it need to perform some work. What is the work? That is the PV work or work done due to expansion. So that would be that some energy is used to perform the work due to the expansion. That energy will be decreased from the initial energy of the hot gas. So that internal energy is converting into the work done by the expansion of the work, or expansion of the gas. So one form to another, it is converting from one form to another. The total energy of a system and surrounding remain constant or conserved. Actually this is the conservation law of energy of the universe. So anything in universe, we have a certain amount of energy. We cannot create or we cannot destroy the total amount of energy in the universe. So just we can transfer from one form to another of the energy. We are using electricity. We are using electricity to generate light or to cook or to produce heat or to rotate the fan. So different thing. We are converting the static energy or the electric energy in different forms. To cook, we are using the heater. To get the light, we are using or we are converting the light energy into light energy. So the total energy of the universe never changes, just it converts from one form to another. So the total energy of the universe is fixed and it cannot be created nor destroyed it. So if we consider the total energy of a system and surroundings, that means anything our consideration is known as system, and anything out of our system, that is surroundings. That means the total universe we are considering as system is our consideration. Like as this is one glass of water, so this glass of water or the glass is our system, and rest of the thing around the system is considered as surroundings, including the all over the world, all other planets, whatever. So that is our surrounding. So the total energy of a system and surrounding remains same and constant. It is impossible to construct a perpetual motion machine. That means you cannot generate a 100% accurate. It is impossible to construct a perpetual motion machine that can produce work without spending energy on it. So what does it mean? You cannot generate a machine which can work 100% efficiently. Let us consider we have certain light bulb. Previously you had a light, like as maybe we have 40 watt or 100 watt, different types of round bulbs, what we call as dim light or whatever is like this. So that light uses huge amount of electricity and we get very small amount of energy or very small amount of light. So nowadays scientists have developed another types of light which is called LED. So LED light has the possibility or ability to convert the electricity to more light energy. So previously if you had a 100 watt light bulb, now you can use around 18 watt light bulb to get the almost same or similar energy or similar light. What does it mean? The 100 watt light, that means if you use one light with a 100 watt power, if you use for 10 hours, if you use for 10 hours a 100 watt bulb, you will use 1 kilowatt hour. That means 1 BOT, that means 1 board of trade unit. So if you use 10 hours, only 10 hours, you will use 1 unit of electricity. But if you use 18 watt or 10 watt bulb, then how long you can use? Any of you? I have given you the calculation that if I use a 100 watt light for 10 hours, then we can use the amount of use of electricity is 1 BOT, that means 1 board of trade unit or 1 unit. Exactly what we pay, that means if the electricity bill is around 10 unit or 20 units or 100 units, so you need to pay against that unit and some other charges what we have. So the electricity, spend of electricity for a 100 watt light bulb, if you spend for, that means if you have an instrument having the capacity 1 kilowatt, that means if you have the energy 1 kilowatt and if you use 1 hour, in that case you will use 1 unit of energy or electricity and the amount of expenditure will be 1 unit or how much money against that. But if you use 100 watt, then you can use 10 times more. Now if you use 10 watt, that means you can have 100 times more time. So previously we have been using 100 watt light bulb and the expense for the electricity is very high. Now we can use 10 watt light bulbs instead of 1 watt, actually 100 watt. I know you have 5 more minutes, just I am going to finish here, so that will be the last slide. So it is impossible to construct a perpetual motion machine that can produce work without spending energy on it. So what I have been mentioning about the light bulb, so if we want to convert 100% electricity into light energy, that cannot be generated nowadays. Maybe 40% or 50% energy can be converted into light energy, and rest of the rest of the energy is converted into some other forms of energy, like as heat or some other thing. So if you touch the light bulb, you will feel the light is hot. So we don't want the heat, but it is automatically generating. That is the limitation of our instrument, that we cannot generate a 100% accurate light. So it is impossible to construct a perpetual motion machine that can produce work without spending energy on it. So this is the end of my today's class. If you have any question or comment regarding this, you are welcome.